So in this short video and the next video, I'm gonna show you two motivation examples about how to use the real data, and hopefully you can use this as a motivation to understand what's the machine learning about. The first data set is come from a credit card data set. As you can see from this scatter plot, the x-axis shows the each debtor's information, the balance in his account, and income information about the debtor. So for example, let's say there's a blue circle here. Blue circle here. So this represents that this debtor, his annual income is about $60,000, and his credit card balance is about like $200. Okay, and this blue color. Okay, I'll use the blue one. Smaller dot. So this blue represents the reliable debtors. Okay, and this orange one's cross color represents, I will use the smaller dots. Small represents defaulted debtors. So the blue one means the debtors always pay back their credit card account on time, and defaulted debtor means at some time point they have some history, they fail to pay back their credit card account. So now the question is, suppose we have a new applicant. Okay, suppose you are the one who working in the bank, and to evaluate each, I think at some time point everyone has credit card, right? When you apply the credit card, the bank collect your information. For example, we have a new applicant who applied the credit card with a balance $1,500, and his annual income is above $60,000. So the question is how to classify, because we don't know any. That's all the information we know about this applicant, but we wanted to know what's their future behavior. Is this new applicant gonna pay back this credit card on time, or he may have the high risk to be defaulted debtors? So that's a question of the classification. So predict. So we want to predict. New applicants. Okay, to be debtor or to be defaulted, to be reliable or defaulted debtors. Okay, so think about it. How do you gonna classify this? Probably if you know the candidate is here, probably you can classify him as a reliable debtor, right? If this guy is around here, this new applicant is here, maybe he has a high risk to be the defaulted debtors. But how can a machine to decide, to make the decision rule? Because each, those like Amex or Chase credit card, each day you have the hundreds or thousands of the applicants. You want to use the machine to filter the applicants first, right? So how can a machine to tell that? So maybe let's say more simplified example here. So the problem is here we have some data. We have the x-axis and we have y-axis. X-axis, you can think this is one attribute in your data set, balance, say. Y-axis is represents the income of the person. So now suppose we have this data set, we can draw the scatter plot. Okay, suppose this is the scatter plot of this our data set. Okay, and we have the blue circle represents the reliable, they are reliable customers, and we have the orange cross one. They are the high risk. Defaulted debtors. So now the question is, how do we find a classifier? A simple rule to let the machine to tell if this new applicant is can be qualified for this credit card, can be approved or not. Okay, so the question is clear, right? Think about it. How do you define the classifier here for this example? Okay, maybe there are two simple classifiers come to my mind. Is the one is we can just use a, you can think we can use a simple rule, right? Simple line, right? For example, seems based on our data set, all the data points on the right hand side of this line has a high risk to be defaulted applicant, right? So this line could be our decision boundary. This is called decision boundary. Okay, so this tells us if we have a new applicant, have question mark. If it's located on the one side is decision boundary, we're gonna classify as a reliable applicant, so we give him approve. If the applicant on the right hand side, we say this guy maybe has a high chance to be defaulted applicant, so we give him decline. And this, if we just use a simple linear classifier, okay, this is called the linear classifier. Linear classifier. Okay, so that's the first case. Is there any other ideas how to classify these points? For those who maybe took my principal data science and data science computing class students, we also, at that time, we introduced some other classifiers. It's called the nearest neighborhood classifier, right? Nearest neighbor classifier, which means for if we have new applicant, we just check which applicant, which data point in the training data set is the closest to our new data point. For example, for this data, maybe this one is most closest one, right? And then we just using the closest color to label this new point color. For example, this one we're gonna classify as a default, okay? But suppose we have a data point here, even it's on the right hand side of this linear decision boundary, but the closest point is a blue dot here, so we classify him as a blue, is a reliable debtor. So we introduced two classifiers. One is a linear classifier, one is a nearest neighborhood classifier. Okay, now we can apply these two classifiers to this real data set. I think in the next homework, we're gonna have some data demonstration using this data set. On this plot, on the left-hand side, you can see this is a result decision boundaries for the linear for the nearest neighborhood classifier. Okay, nearest neighborhood, nearest neighbor classifier. Okay, on the right hand side, this is a linear classifier. At this moment, we're gonna give you more details about these two algorithms, how to find the classifiers from the real data set. But now suppose you know there is some Python code and you apply this Python code to the real data. These are the two results you get, okay? But now the question is, which one is better? Which classifier is better? Obviously, these two classifiers are different, right? For example, each of the classifier has some advantage. Actually, if you take a more close look at this nearest neighborhood classifier, you can see that. So this classifier correctly classify each point, data point. Training data set. In the training data set. For example, each blue circle means a good is a reliable applicant, reliable debtors, and each blue dot is classified as blue in this if we apply this algorithm, and each orange one, defaulted debtor, is classified as a defaulted one. On the other hand, the linear classifier doesn't satisfy this rule, right? For example, if we apply the linear classifier and we say if any data points above this decision boundary, we classify him as the defaulted one, and below this decision boundary, we classify it as a reliable one. But as you can see here, there are several data points. For example, this blue data point, it is a reliable one, but if we apply the linear classifier, it classified wrong, right? So it didn't perfectly work well on the training data set if we apply the so these two classifier can be think as the two extreme case. One is classified each as good. Another case, linear classifier is a simple rule, but it's possible to make some mistakes. Okay, but which one is better? Do you think the nearest neighborhood classifier is better than the linear classifier? I will pause here for a few seconds and let you think about it. Okay, actually, the nearest neighborhood classifier is not, even though it correctly classifies each data point on the training data set, it's not perfect. There is an issue called overfitting. So overfitting is always mentioned in the machine learning algorithm that it worked perfectly for the training data set, but it could work perfect on training data set. But poorly on future testing data. Okay, actually, let's see one more example here. So this is also one, the plot on the left is called, it's the same as the previous one. So it's nearest neighborhood classifier, okay? But on the other hand, this is, we are using the nearest, 15 nearest neighborhood classifier. 15 nearest neighbor classifier. Okay, what's that mean? This means for each data point, okay, for each data point, for example, a data point on a grid point here, what he do is he just find all the distance between this new point and each point in our data set. For example, this is one, this is one, and then we find the 15 closest one. 1, 2, 3, 4, 5, 6, 7, 8. Probably this one is 9, 10, 11, 12, maybe 13, 14, 15. Okay. And among those 15 data points, we count how many of them are labeled as a defaulted one, how many of them are labeled as a reliable one. And the dominant class, we classify this guy as, for example, here, among 15 of them, 12 of them are defaulted daters. So we classify this new data point as defaulted daters. So as we can see, if we adjust some parameter in our model, we can get a more smooth decision boundary, right? We get a more smooth. Boundary. Probably this will perform a little bit better than, perform better than the one nearest neighborhood algorithm, because this boundary may be more reliable, although it didn't perfectly classify each data point in our training data set. And later on, we're gonna talk about what's the balance of the Bayes variance trade-off. Variance trade-off. Okay, and that's how we're gonna use to decide if your model is overfitting or underfitting. Seems if we're using the linear model, is linear classifier is too simple for the real case. But for this 15 nearest neighborhood, it's between the one nearest neighborhood and the linear classifier. Maybe it's the best. Usually, that's the best model we can choose.